Welcome. This is Ahead of Time Techniques Help You Write GraphQL Libraries. I'm Mike Solomon. I'm a software engineer and a GraphQL consultant. Today we're going to talk about how we can steal some techniques from compilers and apply them to GraphQL libraries. This is a short talk, so we're really going to focus on one technique in particular. Let's start by looking at an extremely simplified view of how a compiler works. Usually code goes in to your compiler, and then machine code or assembly comes out the other side. In the LLVM suite of compilers, we might have C or C++ going into Clang, and then have x86 assembly come out the other side. Note that we're looking at ahead-of-time compilers. Just-in-time compilers work a little bit differently, but we're not really focused on those differences today. In this extremely simplified view, a lot of GraphQL libraries do a similar thing. For example, if we're making GraphQL clients, we have GraphQL coming into some kind of a library, and then we have code coming out the other side. So if we're making GraphQL clients, maybe a query and a schema come in to our library, which might be the GraphQL code generator, or Apollo iOS, Apollo Kotlin, or Relay, any of a number of libraries. And then we generate a GraphQL client on the other side. Let's zoom in on that compiler a little bit and break down some of the separate jobs that it's actually doing. We can easily break it into two parts, the front end and also the back end. The front end will parse and transform the language-specific code, and the back end is actually going to be responsible for generating the machine code for a particular processor. But in order to separate these like that, we need to introduce an intermediate representation so that we have something to pass from the front end to the back end. This intermediate representation, or IR, is lower level than the human code, like C or C++, but it's higher level than the machine code, like the x86 assembly that we're producing on the other side. In LLVM, if we're doing this for C or C++, the front end might be Clang, and the back end might be the x86 code generator. This loose coupling is the most bare bones case for introducing an intermediate representation, but it's going to introduce or unlock some very interesting possibilities for us. First off, if we design our IR carefully, it's going to give us the ability to build different front ends and share the same back end, which will let us support multiple languages. So for example, we might take in some Rust code, pass that into a new front end like Rust-C, and generate an intermediate representation for it, and then actually reuse the same back end that generates x86 code. So this lets us support multiple languages for a given platform. And of course, we can keep adding languages, like we might add Haskell, use the GHC front end, generate an intermediate representation in LLVM, and generate x86 code from that. But that's not all. We can also add new backends and thereby support multiple hardware platforms such as ARM. So we can take the intermediate representation, create a new backend, the ARM code generator, and generate ARM assembly from that. So taken together, this avoids the combinatoric explosion of each programming language needing a custom implementation for every hardware platform. There's also another very cool option that this intermediate representation unlocks as well. We often want to optimize our code so that it runs faster and more efficiently. If we do this at the IR level, we can actually share optimizations across programming languages and across hardware platforms for free, in the sense that we only have to implement them once. So in LLVM, we might take the intermediate representation, pass it to a middle end, which is really what they call it, and generate IR from that on the other side in kind of a loop. So hopefully by now you can see at least some of the advantages compilers get by using an intermediate representation, but you might be asking, what is it actually? So let's make it a little bit more concrete. In LLVM, it's actually an assembly language with rich information attached. So if we have some programming language like this pseudocode, and we have a function f, we might generate some LLVM assembly, which is their intermediate representation, that looks something like this. We're not really going to dig into this at all other than noting a few properties here and there. The types are preserved. You can see it takes in a double, and that's preserved throughout the assembly. It's strict and it's simplified. This uses static single assignment, which is useful in compilers, maybe less useful in GraphQL. But it's human and machine readable. You can, with a little practice, you could probably get pretty fast at reading this intermediate representation, but it's also easy to manipulate programmatically. If you're like me, you might be saying that's all well and good for compilers, but we're at a GraphQL conference, so how does this apply to GraphQL? What does a GraphQL IR do? Well, it's going to work similarly to the compiler that we've been looking at. It takes in GraphQL, probably in the form of a query and a schema. That goes into a front end, which parses and transforms it into an intermediate representation, and then we can pass it to various backends. For example, if we wanted to generate an iOS client in Swift, we can pass it to a client generator that targets that particular language and get it out of the other side. From here, we can use the same techniques we saw in compilers. We can target separate backends, say by generating client bindings in other languages. So if we want a GraphQL client in Kotlin, we can add a new backend generator for that. And we might even have some other or we might generate other things besides just GraphQL clients. Like we might want some serializers or deserializers for data formats like JSON or Argo. And you can imagine some other use cases too, maybe some metrics or error analysis, linters, that sort of thing. And we might also have some opportunities to optimize at the intermediate representation level. For example, maybe we statically skip or include fields if arguments are already known. And this gives us like a pretty similar picture to what we saw with LLVM. I always think it's helpful to look at an example. If you're asking yourself, can I see it? I understand. It's worth noting before we look at one that we don't share any kind of common intermediate representation for GraphQL, even though several libraries use this technique or something like it. So we're just going to look at one from a particular library that I happen to be familiar with. This example is taken from Argo, which is a compact binary serialization format for GraphQL. If you squint at this, you can see that it shares the shape of a query response with lots of extra information added and inlined. It has some of the same properties we saw with the LLVM intermediate representation. Types are preserved. It's strict and simplified. It's both human and machine readable. So I'm not advocating that we start using this particular intermediate representation for all GraphQL libraries or anything like that, but hopefully this makes it a little bit more concrete about what it might look like if you're using this technique in your library. Lastly, I just want to highlight some existing GraphQL libraries that either use an explicit intermediate representation or have some kind of similar idea used inside them. This is not exhaustive by any means. But Relay has Relay compiler that has an explicit intermediate representation. Argo uses the one that we just saw. I was talking to some folks who said Hasura uses an intermediate representation in their products. And then here's a list of some others that I found. You can get a copy of the slides from the conference website and check out these links if you want to actually dig into some of that GraphQL intermediate representation code. And I hope this inspired some of you to check out this or other techniques from compilers you can use in your GraphQL libraries, or maybe it explains some design choices that you've encountered in libraries like these here. And with that, I'm going to close. Thanks very much for coming. If you have any questions or if you'd like to talk about it, come and find me. I'd love to chat about it. I also do GraphQL consulting, so if that's something that might help you out, come and find me. Thanks. I think we have time for a question or two. Did you have a question?
Yeah, I did have a question. I guess I'm so kind of mostly interested. I see all these applications are actually more like kind of client-side focused applications. Have you ever thought about using kind of the more compiler-based approach for server side and then say kind of improving the execution and performance of the
Yeah, my background is much more in back-end services. And when I worked at Twitter, we did something kind of similar to this that had, you have to squint a little bit to call it an intermediate representation because it was all kind of all powered by this internal programming language we had. But that was kind of my entry into this whole space, I think. And in that context, we were doing it to do automatic batching, both from GraphQL APIs, which can be very important for the performance of GraphQL APIs, but also from other internal systems that weren't using GraphQL at all. So yeah, definitely, I think you can apply a lot of these same things in that context.
But not in a sense like you're actually, so today most GraphQL executor run it in interpreted mode, right? Right? Interpret the query, evaluate it as you go. It's not like you're actually.
Yeah, that is true. I think there's room for applying that on the server side, though. I think you could. Sorry, I'm not repeating the question. You could probably generate code or something on the server side instead of interpreting it every time, and thereby benefit from a lot of ahead of time techniques. You could kind of do like a server side code generation beforehand, for example, and then rely on your actual compiler to do various optimizations. And then batching, you'd have to do something else about. Cool. Yeah, what's up?
You mentioned that this is used today in different libraries, but with different internal representations. Would you see value in this becoming standardized, say, as part of the GraphQL spec?
I would want to see. Would it be useful to actually standardize one of these intermediate representations and share it across many libraries, maybe as part of the spec? I think I would want to see it used successfully in multiple libraries before it got into the spec, just in the interest of it validating its usefulness across many diverse spaces first. But I think that could be useful. A lot of these libraries do use this technique, and usually what they're doing is taking the GraphQL query and schema, kind of like inlining and combining them, maybe simplifying a bit, and making all that information available immediately. That sort of thing maybe has potential for reuse across lots of libraries. And if that turned out to be true, then yeah, maybe sharing it across multiple projects through the spec would be useful. Any other questions? All right, great. Thanks very much.